Welcome everyone. In this video lecture, we will think about the resistively loaded NMOS inverter and the concept of noise margin. So, there is a figure in which we can easily identify there is a NMOS transistor. Okay, so in this NMOS transistor, this in the air connected in is our source in, and this in is our drain, and this one input we are giving to the gate in. So this one behaves like a inverter. How that we have to think out. Okay, so we are giving the VDD supply, adding the resistance, we are taking output across the drain in and giving input to the gate in. Okay, so if anyone have to plot the graph between V naught, okay, it is a output voltage, and input voltage say Vi. So what we have to do, if this transistor have some threshold voltage, say VTN, okay. So when the input voltage Vi is less than VTN, okay, VTN is nothing but simply our threshold voltage. So I'm writing threshold voltage. Okay, so when I am saying this vi this vi is less than vtn, then the transistor, that is our m1, will be in cutoff mode, cutoff mode. Okay, and id current, cutoff mode. So the id current will be, id will be 0. Okay, very simple. So we can easily identify that V naught value will be same as that of ID. So we can write it V naught is same as that of VDD. Why? For this purpose, I am just redoing the circuit. This one is VDD, okay. This one is RD, and some current is flowing, say ID, okay. So this voltage, if this one is zero, so sorry, this voltage is when VDD. So the ID current will be VDD minus VDD by RD. So that's why this was the 0 volt, sorry, 0 ampere current is flowing. Okay, so the 0 ampere is current flowing. So we can say that the output voltage is more or less VDD. Okay, and after that, up to which level? Up to which level this one is VDD? Say I am saying this one is our VTN. Okay, up to this one, the output voltage will be same as that of, we can say that this one is VDD, or we can write it VOH, output high voltage. After that, what we observe that now we consider the extreme condition when the input is very high, when we are saying Vi is say VDD. Okay, one condition when Vi is less than VTN, this one 0 ampere. Okay, when input is very high, so this will be more or less on, transistor on, M1 on, but I am not telling it is in cutoff or linear, sorry, saturation or linear, that we have to decide. M1 on, and the V naught value is nearly to 0 volt, nearly to 0 volt, because this one will be sorted, and this should be nearly equals to 0 volt, but not exactly 0. So what we observed, that after that this type of thing will happen. So this point I am saying VDD. So we can clearly identify that this region is our cutoff region. Okay, but for the other region, means saturation and linear will lie in between. Okay, so we have to know the conditions first. So I am just drawing the characteristics, that is our id and vds characteristics of a NMOS transistor, and it looks like, okay, so this point I am saying VGS minus VT. So as we know, when VDS is greater than equals to VGS minus VT, is it in which region? Saturation. This one is a fundamental concept. So this one is in the saturation region, okay, and this one is in the linear region. Okay, linear region. Yeah. Now this one is a saturation. Now for the linear, VDS will be less than VGS minus VT. That is our linear region. So this one is very important. Everyone have to know. Okay. So now so actually in this case, if we assume that VDS, suppose I am writing that VDS is greater than VGS minus VT for saturation region. So we can also write VD minus VS greater than equals to VG minus VS minus VT. So this VS will be cancelled out. Then VD is greater than equals to VG minus VT. Now we can place VD is nothing but simply our V output. So V output is greater than, suppose, Vi minus Vt. Now, if V naught is greater than Vi minus Vt, okay, so it is in the saturation region, okay, and when this V naught is less than Vi minus Vt, it is in the linear region. Simple concept, linear region, okay. So now what we observe that, suppose some point is there, say V, any point take, suppose some point say V dash, okay. So when the input is V dash, when the input is V dash, this value will be V dash minus Vt, and this V dash minus Vt up to this point, now the output voltage is decreasing, okay, but for this up to this point, this V naught will be greater than Vi minus Vt. So this point will be considered as, up to this region, it is considered as a saturation. Okay, and after that it is comes under the linear region. Here linear region. Once again I am repeating this concept. When some V dash point is there, okay, so up to V dash, okay, V naught is somehow, suppose this one is VDD, and it comes down, say this point, for that time being I am saying this point is less than VDD. So I'm just doing for V naught greater than Vi minus Vt. And say this point is say 5 volt, VDD is 5 volt, and this point is say 2 volt. For example, 2 volt I am writing. So this one output is 2 volt, okay, and here this V dash point is around 2.5 volt, and for the threshold voltage I am saying, or better to write this as a 2.4, and this value will be say 0.5 volt VT. Okay, so this value 2 will be greater than 1.9. Okay, so up to this one, so this V dash, that is our VI, is now considering around 2.4 volt. Okay, so this 2 is greater than 1.9, so this one will be acts as a saturation region case. But when we exceed the input voltage greater than 2.4, greater than 2.4, so this output voltage, so this in this case this one is in the saturation region. It is very important to analyze this type of one. So now when the VDS value is greater than 2.4, okay, so output value will be less than Vi minus Vt, because in this case now if we are taking any point, okay, so say this value will be say 1.8, okay, by assumption. So 1.8, then the Vi value, that is our V dash minus take this value will be 0.5. Okay, so this one is 1.8, and V dash value will be increased to 2.4 to say 3 minus 0.5. So it should be 1.8 volt is less than 2.5 volt. Okay, so it is correct. So this one is the case when this is in the linear region. So during that time it is in the linear region. So this one is a very important concept that we have to know in which region this is cut off, saturation and linear. So it is somehow it's as a inverter characteristics. Okay, so what we can assume that by considering this voltage, okay, so the initially it is in the cutoff, saturation, then linear. Okay, so now if we plot the same curve, here I am again doing the same thing. So this one is our what, output voltage, input voltage, then say this one is a VOH. Okay, and this one is our output low voltage, and this value will be considered as a input low value, and this one is a VIH, and this one is some high value, that is our VOH. The same thing we are doing, but here we can say this one is in the what, cutoff region. Okay, and after that it is in the saturation. Okay, for some point. Okay, and then it is in the linear region. Okay, so now what we have to do, and this point we can say this as a VOL for the concept noise margin. What we can say, this one, this distance, this one, that is our NML. Okay, and this one NMH. Okay, so this one NML, which is nothing but simply noise margin for low input. I am writing here NML is nothing but simply noise margin for low input. Okay, low input, and this value will be our VIL minus VOL, and NMH, noise margin for high input. That is our simply VOH. So no need to remember the formula for noise margin. Okay, better to draw these characteristics. Okay, VOH, right? VOL. Okay, then this input will be VIL and this value will be just VOL. So better to write here. Suppose this one is 2 volt, so this one is also 2 volt. So that's why I'm doing like that. And then we can this one. Okay, and the other parameter like our VOL is the output. I'm writing output low level. Okay, VOH is better to write output. That's why I'm writing output high level. Okay, and the two parameter are there, VIL and VIH, and this one is very important. VIL. So first we have to think about VIL. VIL is the maximum input. Okay, VIL is the maximum input that will give the inverter value to a logic high. Okay, or we can say maximum value of input. Maximum value of input, I am writing maximum value of input by the inverter. Okay, maximum value of input by the inverter to get the output value high. Okay, means maximum value of input. If we give any value in between this one, it will contain the maximum output value, or we can say maximum input given by the inverter as a logic 0. It is considered as a maximum input value given to the, or we can simply write one more thing, we can write maximum value of input given to the inverter, through the inverter as a logic 0. Okay, maximum in value of input given through the inverter as a logic 0, maximum. Okay, but here the other term, that is our VIH. So this VIH is the minimum. We can write minimum value of input given through the inverter as a logic 1. Okay, and that time it will give the output low value, here output high. Okay, very simple facts is that VL is the minimum, not maximum, sorry. VL is the maximum input given to the inverter as a logic 0. VIL maximum input as a logic 0 input, and this VIH is the minimum input as a logic 1 high. Okay, so easily we can find the NML. Okay, noise margin for a low input, that is our VIL minus VOL. From here we can say N NMH equals to VOH minus VIH. Okay, so this is the very important concept regarding the noise margin. Okay, to understand this concept, we can follow one example. Okay, for the noise margin. So basically, I'm taking this concept from the Shedda Smith book. So first I have to make, suppose there are two inverter. So I am just making two inverter block. Okay. Say inverter, inverter number one. Okay. And another is our inverter two. Okay. And these two inverter are connected. Okay. And in between we are giving some noise. Say Vn, and this the output is nothing but simply VO1 for inverter 1, and this is a Vi2. Okay, so what should be the value of Vn that we have to think of? Okay, so we are giving some input, we are not giving the, say this one, say input anyone, input 1. Okay, and say output 2. Okay, so our main focus is in the middle. So we can simply say the value, input value, that is our Vi2 to the inverter 2 as a input will be V01 plus Vn. Okay. So now what we have to think, if the, now this one is the input value for the second inverter, input to the second inverter. So now output value, that is our V01, will be either VOL or VOH. So consider first case, case 1, when V01 is a VOL. Okay, so when we are considering V01 equals to VOL, so Vi2 will be VOL plus Vn. Okay, this one is the case. Now again I am drawing the characteristics V0, Vi. Okay, this value will be V0, this will be our VOL. So we can write this as a VOL, and this value will be our VIL, input low, and this will be VIH, and this will be our VOH. Okay, very simple. And this one is our NMH, and this one NML. Now Vi2 will be VOL plus this one is noise signal. Okay, it may be positive or negative. Okay, so for proper functioning of this inverter circuit, okay, the Vn value will be what? If this noise will be VIL minus VOL. Okay, so if this value will be VIL minus VOL, so it will give the input low. So maximum value of the noise will be VIL minus VOL, and during that time it will give a low input. Okay, so this one is one option, one case. Now in case of case 2, when this one is V naught H, then Vi2 will be, just put here, VOH plus Vn. So now this again here in this case, this one is our positive value, Vn is positive. Now VOH plus, if we go above, it will work. But when we are saying VOH, okay, so it will, if this value will be VIH, then it will work properly. So then Vn value will be just negative of this value, what we can write? VOH minus VIH. So in this case, the acceptable limit of the noise in between minus VOH minus VH. So it will come VIH. So the noise value will be VO minus VOH minus VIH. Very simple concept is there, but you have to remember this graph. True, then for case 2, this VOH, and for case 1, VO1 equals to VOL. So the noise value will be negative. Noise value will be negative. In case of VOH, the noise value will be negative. That is our minus VOH minus VIH, because in this case it becomes VIH. Okay, we have to maintain to VIH, and we have to maintain to VIL. So VIL will be, if simply you write positive, will be VIL minus VOL. So it should be VIL. So the value for the noise will be VIL minus VOL, and this one for the VOH value negative, because this VIH will be cancelled out. So it should be VOH. Okay, so this is all about the concept. So for more detail, you can also follow the very famous book Microelectronic Circuits, Microelectronic Circuits, okay, by Sid Smith. Okay, so this is all about this video. I hope some points will be clear out. And for more detail, go through that book and also follow my earlier video. So thank you for watching this video.